Alright students, so we are talking about the composition of functions, and we're going to be looking at some advanced type questions here. So before we actually dig into the problems, we're going to consider a somewhat basic example here. So we're going to consider the domain and range of two functions as well as the domain and range of their composition. So we've got two functions, f and g, and we're going to consider f composed of g of x. So to make things simple, we're going to start off here and just define g very plainly here, where g of 0 is equal to 2, g of 1 is equal to 4, g of 2 is equal to 8, g of 3 is 16. So just a real basic mapping sort of relationship here. So the domain, and by the way, this is it. That's all there is for g. It doesn't go below or above or anywhere those values in between. So our domain is literally just 0, 1, 2, and 3. And the range are going to be these values over here. So 2, 4, 8, and 16. And we can draw that mapping relationship right there between them, like so. And now let's talk about f. Sorry about the bad handwriting here. So we have f of 0 is 5, f of 2 is 10, f of 4 is 20, and f of 5 is 30. And just for fun here, f of 8 is also 30. So just sort of mapping the x and y values there, so to speak. So I think we're going to erase this, put it over there on the other side. So thinking about f, the domain of f are these values that we can plug in, 0, 2, 4, 5, and 8. And the range are going to be these y values, so to speak, the 5, 10, 20, and 30. And we can draw the mapping diagram there. Okay, so let's go ahead and consider some different values here. So let's consider f composed of g of 0. Let's think about what that actually means. Okay, well, if we look up here at g, and if we plug in 0, then that's going to give us a 2. So this inner expression right here, g of 0, I can just simplify to 2, the number 2. And then if I now evaluate f of 2, I go over here and I say, okay, there's 2. Well, f of 2 is equal to 10. So that's my answer. F composed of g evaluated 0 is 10, utilizing these mapping diagrams. All right, let's do another few of those just before we kind of think about the domain and range of the composition. So f composed of g of 1. Well, g of 1 is equal to 4, as we see over here. So that would mean I have f of 4. All right, if I look at the function here, f of 4 is equal to 20, so that can be simplified there to 20. In the same way, f composed of g of 2. Well, g of 2 is equal to 8, so I can simplify that to 8, and now I have f evaluated at 8. So that's down here, f of 8 is equal to 30. Okay, that's great. F composed of g of 3. Actually being quite exhaustive here in my situation. So that's, well, g of 3 is 16, so f of 16, well, it's not listed in the domain, so that's not an acceptable input for f, and so we would say that does not exist. Error, not, that value is not in the domain of f. So if we were talking about the domain of f composed of g of x, so this new function, what we're looking for is all the input values, or all the domain in g, all the values that I'm allowed to put in here, that actually have a path through to the range of f. Wow, that is horrible, right? To the range of f. So everything that basically, every x value here that I can put in it, and I can trace that all the way through, and I end up with a value here. So I'll erase these stars so we can kind of go through here a little bit better. So 0 goes to 2, and 2 of input is allowed, and I end up with 10. Okay, so 0 is an acceptable part of the domain of f composed of g of x. Now let's trace the 1. 1 goes to 4, 4 goes over here, and so, yep, 4 leads to 20. So in fact, 1, that starting point, is also part of the domain. I can put a 1 inside this inner function here. If we look at 2, 2 goes to 8. 8 is part of the acceptable domain of f, and that goes to 30. So, in fact, 2 is also part of the domain. 3 goes to 16, and we saw that doesn't go anywhere, so it's not allowed. So, a couple things to note. The domain of f composed of g of x is not everything that's in the domain of G. Because 3 is not part of this domain. In fact, it's also not everything that's in the domain of F, because 5 is part of the domain of F, but we can never get to 5. And so, and that's not really the point. I'm looking to see what values I can plug inside here of this G of X. So the domain of F composed of G of X is just 0, 1, and 2. Kind of along the same lines, the range of F composed of G of X is all the reachable range values here in the outer function, so here in F. So in this case we can see 10, 20, and 30. Those are all reachable. I can get there. 5 I could only get to from 0, but 0 is never going to be part of the output of G. It's not part of the range of G, so I can't get to 0, so therefore 5 is not part of my the range of this composition function. So 10, 20, 30, that's it. There's the domain of F composed of G, and there's the range of F composed of G. Now let's maybe look at something a little bit more legible. Here we go. Two functions, G and F, are defined in the figure below. So there's G and there's F. It's kind of in the same order that we had a moment ago, which is good. This says find the domain and range of the composition F composed of G. Write your answers in set notation. Okay. Well, F composed of G means F on the outside and G on the inside. So here we go. Let's start tracing through. So 0 goes to 2, and 2 is allowed here on the input, and there's 8. So I'm going to circle these when they're in. 1 goes to 9, and that's a dead end. We cannot have 9 as an input of F, so cross that out. So no. 4 goes to 7. 7 is allowed as a domain. 7 goes to 8, so I'll circle the 4. 5 also goes to 7, which, as we saw, leads to 8, so we'll circle that. 7 as an input goes to 6, which is tied to 1 with the final output. So 7 gets circled. 9 goes to 9, and also that's a dead end. So the domain, as we saw, are all of the domain of G here that have a path all the way through, which happens to be 0, 4, 5, and 7. The range are the reachable Y values here, so that's 1 and 8. That's it. We're done. So we'll look at this one. It's a little bit different where all these values are pointed the same. So same question. Let's trace this through. 0 goes to 5. 5 is a dead end. 0 is out. 2 goes to 6. 6 will play. So circle the 2. 4 goes to the 1. 1 will play. Go to there. 6 goes to 0. 0 goes to 2. So yep. 8 goes to 4. And that's a dead end. There's no 4 here allowed as the input. Oh, by the way, this is G composed of F. So they just switched the letters here, but that's okay. 9 goes to 2. 2 is allowed. So here we go. So the domain is everything over here that plays all the way through. So that's 2, 4, 6, and 9. And the range is just 2. That's the only one that's allowed. It's the only one that's reachable, I guess. So we're happy about that one. All right, so there's your mapping diagrams. Those are the, I don't know, maybe you could say the easy ones. I like them because they're visual. This next problem here says for the real valued function f of x equals x minus 6 over x minus 3 and g of x, 2x minus 1, find the composition f composed of g and specify its domain using interval notation. All right, so this is where we're going to put our answers. So f composed of g of x, I'll just write that up here using this sort of, I think, a little more friendly composition notation, f on the outside and g on the inside. So g of x is 2x minus 1. So that means that every time I see an x up here in f, I'm going to say 2x minus 1. So here we go. 2x minus 1. Oh, yep, gonna plug those in. Okay, so, oh, excuse me for a second. What we did here was I just went, instead of writing g of x, I wrote 2x minus 1 here inside this parentheses, so I could sort of simplified it. Now, I will substitute 2x minus 1 into those x values. So here we go. 2x minus 1 minus 6 over 2x minus 1 minus 3. Notice just substituting those in. This is a good point to sort of pause and to deal with the domain, because one of the rules about specifying the domain is we have to do this before we do any simplification. In this particular problem, that isn't going to make a difference, but we'll go ahead and follow that procedure anyway. So the situation with rational functions when worrying about when there's a domain is when the denominator cannot equal 0. So that's 2x minus 1 minus 3 cannot equal 0. So 2x minus 4 cannot equal 0. 2x cannot equal 4. Ergo, x cannot equal 2. If I think about what that means on number line, it means I've got 2 right here with an open circle, and everything to the left and everything to the right is allowed. So writing that in interval notation means I've got everything from negative infinity all the way up to 2, union with everything from 2 onward. Parentheses there because 2 is not part of that set, or part of that interval, I guess. So that's the domain. That's actually technically the answer to part 2 there. And then the other thing they want us to do is they want us to simplify this now, and that'll give us the actual first part here, f composed of g. So minus 1 minus 6, that's going to be just minus 7, and minus 1 minus 3 is 4. So there you go. That is our simplified expression for f composed of g of x. All right. Let's go ahead and scroll down just a little bit and look at this next problem. So here we have same kind of thing. F is 4x plus 3, but g now is square root of x minus 4. Once again, find the composition and specify its domain using interval notation. So I always like to write this f composed of g as f and then composed of g. Then just from the next step, just write square root of x minus 1, just sort of simplifying that. It really helps out, I think, to see what's going on, and it makes the process more likely to be free of errors. So now I have this expression, square root of x minus 4, and I'm just going to plug that in every time I see an x, which happens to be just once. So here we go, 4 times square root of x minus 4 plus 3. All right. So when we think about the domain, when you got square roots, what that means is, everything that's this notation is not correct. I should have said that the stuff that's inside the square root, the dot 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 there, has to be greater than or equal to 0. So I just erased that because I felt like that was a little ambiguous there. Incorrect, actually. So x minus 4 has to be greater than or equal to 0. Otherwise, we end up with imaginary numbers, and we don't deal with that right now. So we had 4 to both sides. We have x greater than or equal to 4. Think about that on number line. So solid circle there at 4, and we're everything greater than that. So that would simply be just bracket 4 to infinity. Remember, parentheses always round infinities and negative infinities with interval notation. There's the domain. And then this will really make you smile. That's the function. We can't simplify this anymore. We can't square it or rationalize the denominator or anything like that. Factor this. That's a good answer right there. 4 square root of x minus 4 plus 3. All right. This next problem says for the functions f of x is 1 over x minus 4 and g of x is 11 over x. Find the composition f composed of g and simplify your answer as much as possible and write the domain using interval notation. It's the same kind of thing, but now we've got rational. Both of them are rational expressions. No big deal. So f composed of g of x. So once again, just rewriting g of x as the actual expression here, the function rule 11 over x. And that means, once again, that every time I see an x over here in f, I'm just going to say 11 over x. So here we go. 1 divided by 11 over x minus 4. It is at this point, as soon as I first write the unsimplified version of the function rule, I want to deal with the domain. If I simplify this a little bit, then I can end up with some situations that actually I would allow numbers in the domain which shouldn't be allowed. So remembering here that we don't want anything in the denominator to equal 0. So that's kind of interesting because I have a fraction of fractions. I've got a big fraction, 1 over this thing, and then I've got another fraction over here, 11 over x. And the thing is that neither one of those denominators can equal 0. So I'll start with this smaller fraction right here. Oh, that's just me saying before the simplification. Yeah, we're ahead of you there. So obviously x, which is in the denominator in this smaller fraction, cannot equal 0. That's not too hard to deal with. And then also this fraction, or this expression right here, 11 over x minus 4, cannot equal 0 because that is in the denominator of the large fraction, so to speak. So just do some math here. Add 4 to both sides, multiply both sides by x, end up with 11 equals 4x, divide both sides by 4, you get 11 over 4. So x cannot equal 11 over 4, which is, almost 3, like 2.75 or something like that. So anyway, here's 0, and here's 11 over 4. Well, let's use the fraction. That's fine. I'll have an open circle on each one of those, but everything else is allowed. Okay, x can't equal to 0, and it can't equal 11 over 4. And I love writing it with a number line here because then it makes it really easy to write my interval notation. So we've got from negative infinity up to 0, the union 0 to 11 over 4, union 11 over 4 to infinity. I've got parentheses here rather than brackets because it was an open circle. And that's our domain. The next step is to simplify our answer. So fractions of fractions apparently aren't simplified. So gotta find some space here to write the problem. Okay, maybe right over here. So I have 1 over, and what we'll do is we'll find a common denominator right here. So common denominator of x maybe. So I'll multiply that 4 times x over x. All right. And then kicking over here to the side, I have 1 in the numerator, then 11 minus 4x, that's subtracting the numerators there, over x. And then, instead of having a numerator divided by a denominator, I'm going to write the numerator times, flip it, the reciprocal of the denominator. So x over 11 minus 4x. And 1 times anything is the anything. So we have x over 11 minus 4x. That's the answer for our simplified version. Good job. The last 2 problems are technically word problems relating to the composition of functions. Okay, it's just it seems like it's a little bit forced, but whatever, we'll do it. So essentially, we're going to have one function, and then we're going to have another function, and we're going to take this function and make it the input of that function. There you go. That's it. So the braking distance d of v in meters for a certain car moving at velocity v in meters per second is given by this function. Notice it's d. The output is the distance, and the input is the velocity. And then they can't use v right here because that would just be weird, but it makes most sense. But it says the car's velocity b of t in meters per second, t seconds after starting, is given by b of t is 3t. So whatever, let's just call it v. The velocity as it depends on time. There you go. Okay, it's 3t. Write a formula for the braking distance. Yeah, see, similar. S of t. Now you're like, well, isn't the braking distance d? No, d with a capital D there is defined as the distance as a function of velocity. They want us to write the distance as a function of time. Okay, well, that's no big deal. So all that means is we're going to substitute in 3t to where we see the v. All right, so if you want to think about it in terms of composition, that's d composed of b, whatever. Okay, we're just plugging in the 3t. So 3t quantity squared divided by 34. That's actually the answer. Just take this value, plug it in. Let's go ahead and wrap this up here. This one says the volume of v of r, so velocity is a function of r, of a spherical balloon with radius r meters is given by v of r equals 4/3 pi r cubed. The radius w of t, okay, let's just call it r, after t seconds is given by r of t is equal to 5t plus 3. That makes the most sense. Write a formula for the volume m. Okay, well, maybe we should think of it more like v, but anyway, cubic meters of the balloon after t seconds. So notice this is now velocity as a function of the radius. We're going to make this velocity as a function of, or sorry, not velocity, volume. Volume as a function of time. So I'm going to take this 5t plus 3 and substitute that in for r. So we have 4/3 pi and then 5t plus 3 cubed. Boom. That is the volume as it depends on time. There we go. All right, so we talked about composition of functions. Here we have just sort of in a sort of a word problem situation. We dealt with radical expressions, rational expressions as well, finding the domain, simplifying them, as well as those mapping diagrams. So I'm real happy. Hope you enjoyed this, and good luck solving these problems on your homework.